Alright folks, this video is about rotational kinematics. I'm also going to adjust the camera at one point in time to look at the rotating platform again, so just be aware that you'll see some jostling. So we're focusing on kinematics first. Rotation is kind of like a review of all of physics through the lens of things that are spinning. So we start with kinematics, and so the point of kinematics, if you remember, was just to describe the motion of objects. And so we talked about things like position, displacement, velocity, and acceleration. And so we learned all the linear versions of those variables. So in kinematics, the variable for position was x or y or z, and it had the units meters. And so something can have a linear position, and it can also have an angular position. So we'll get to that later. If we're talking about displacement, we're talking about an object that has moved. We use delta x to describe its displacement, so change in position, and that's in meters. We've also used x minus x naught. Velocity, v, and units meters per second. So how much distance does an object move every second? And then acceleration is lowercase a, and that's in meters per second squared. By how much does the velocity change every second? And so things that are rotating also have angular values for all of those kinematics values. And if you actually think about any one point on a rotating object, it has all of these variables. It's going to be 8 variables that can be used to describe the motion of the object. Okay, so angular version. So the angular version of position, if we think like, here's an object right now, I can describe, like from this hole in my ruler, I can measure how far away the numbers are. As far as an angle goes, it's going to be related to a reference. And so if I like start the ruler at a horizontal orientation and then rotate it, the way that I would figure out the displacement would be to measure the angle between where my reference and where the ruler is right now. This angular version has to describe the entire object, especially because we're focusing on rigid objects. And so the linear position is for an object that's in a certain location. An angular position is for an object that is rotated at a particular angle. And so theta is going to be the variable for angular position. You want to think of it as the x-axis is 0 degrees. And so if something is getting rotated like that, this would be the value of theta. And so positive is counterclockwise, because on a graph, you typically start with 0 degrees here and rotate around. The unit for angle is radians. Okay, so that's position. Displacement, same idea. If I take the ruler and I move it by some angle, I've changed its angular position, and so we're talking about delta theta. And that's also in radians. So you can have an object at a particular angle, or you can displace an object by a particular angle. In terms of velocity, there's both a linear and an angular velocity. And so we'll spend a little bit more time on angular velocity, but I can like flick this ruler. And so it takes a certain amount of time to change the angle. And so that's what angular velocity is. The variable is the Greek letter omega. So that's a W that's like kind of cursive. And so you can look it up if you want to see like a better, more finely drawn version of that. But angular velocity is the number of radians that the object rotates every second. And so radians per second. And then just so if you want to remember this, that W is the Greek letter omega. There's a capital and a lowercase version because it is an alphabet, that uses capital and lowercase letters, and so this is the lowercase omega. Okay, so the magnitude of the angle that the object sweeps per second, and then an object can also be rotating and accelerating. The variable for angular acceleration is the Greek letter alpha. It is by how much the angular velocity changes every second. So it's radians per second per second. or radians per second squared. And so that is the Greek letter alpha. So just a quick trip to the rotating platform so that you can see these variables in action. And let's see if I'm any good at this. Yeah, that's not too bad. Okay, so I start the platform from rest, and then I get it rotating. Give it a little push, and hopefully it's encouraged to do that. So at this point in time, it is accelerating. Now, I accelerated it manually, but again, I'm mostly here to talk about velocity, because velocity is the thing that you can probably attach to the most easily. And again, as you hopefully notice, the manila flag is not moving as fast as the blue flag. So the entire object, the entire disk, is rotating at the same rate. So there is one angular velocity for the entire platform and both flags. However, there is a unique linear velocity for every single object here. And so the manila flag and the blue flag have different linear velocities, but the same angular velocity. Now, over the course of this platform has sped up a little bit. If I unplug it, I can make it slow down. So remember that acceleration can be positive or negative. If I remove the power supply from this apparatus, there's no more drive to this rotation, and so the rotation will just slow to a stop very quickly. And so accelerated motion is the increase or decrease in angular speed. And so you can see it's picking up rotational speed as it goes. All right. One last thing, as far as angular displacement is concerned, it is not limited to 2 pi radians. 2 pi radians is the number of radians in a circle, but because these things are rotating continuously, the angular displacement just keeps increasing. So you can have millions of radians of angular displacement, even though the thing isn't actually changing where it is. So again, there's another visual for the kinematics there. And the last thing to do for this part is to focus on the relationships between the two. So and I kind of messed up. I meant to put S here. So I will put S. And actually, yeah, there we go. S is a displacement because it's the arc length that's traveled. So we're going to kind of ignore the linear and angular relationship between position and angle. But as far as displacement is concerned, we talked about this one already. So the arc length is equal to r times theta. So again, what that means is the linear distance that something travels is equal to the distance it is from the axis of rotation times the angle that it's swept through. I suppose that should be delta theta. Oh well. And then the same proportionality exists through the other two. The linear velocity, or the tangential velocity, is equal to r times the angular velocity. So I want this to make sure it makes sense. The entire object can be rotating at the same angular speed, but the further away the point is from the center of rotation, then the faster it's going. And so there's that proportionality that the linear speed is proportional to the distance from the center. And then finally, acceleration enjoys the same relationship, that again, the linear acceleration is proportional to the angular acceleration and the distance from the axis of rotation. The best way to kind of combat all of these ideas is to do practice problems, so that's what we'll be doing in class a lot of. Now, there are linear kinematics data values, variables, and then angular kinematics variables. And so, as you might expect, there are constant acceleration equations for rotation, and they look exactly the same as their linear counterparts because all of the angular variables are related to the linear variables by a factor of r. So if you take your constant acceleration equation, v equals v naught plus at, and you divide the whole thing by r, you get this equation. And so if you take the distance from axis out of these equations, or out of the kinematics equations, you get all the angular equations. So these are constant angular acceleration equations, and again, they have the same pattern for these. They just all have Greek letters instead of, our usual alphabet. Okay, the last, and so we'll work with these a lot in class. They are exactly the same concept, and so really, like, the struggle is going to be these equations right here, I think. Just some additional ideas here. Because things are moving in circles, they also have centripetal acceleration, and so just very quickly, this equation for centripetal acceleration, because something's moving in a circle, it's actually also rotating. And this goes for like a car traveling around a turn, a roller coaster cart doing a loop-the-loop, anything that's actually moving in a circle, you can use the rotation concepts and centripetal acceleration to describe it. So what do we mean by that? We say centripetal acceleration is equal to the tangential speed squared divided by the distance from the center of the circle. Well, the center of the circle is also going to be the axis of rotation. So I can combine this equation with an equation we just learned, that the linear speed is equal to the distance from the center times the angular speed. And if I combine these two, I get this intermediate equation. And if I simplify that, I get centripetal acceleration is equal to r omega squared. And so if I know the rate at which an object is rotating, and I know how far away from the axis something about it is, I can determine its centripetal acceleration. This is also tied to the idea of angular frequency. In the centripetal motion unit, we talked about the speed of an object moving in a circle is equal to 2 pi r over t. So that's the circumference divided by t. And if I apply one of these relationships, v equals r omega, I can again combine my angular idea in here, and I get r omega equals 2 pi r over t. The r's would cancel, and so omega is equal to 2 pi over t. So I have a couple ideas here, or we have a couple ideas. Centripetal acceleration is equal to r omega squared. This is at all times. Even if it's accelerating, if you know the velocity at any instant, you can find the centripetal acceleration. Now, because this equation has period in it, this is for constant velocity motion only. And so their equations, the centripetal one isn't in your equation sheet, but this one is, and I want you to just understand that it's this random angular concept that appears in all of the instances of period that we have. And so those are kinematics. We'll be working with those equations in class, but that's your intro for now.